process repeats. So every new history vector depends on the previous history vector and the value of the input at current instance. The output is then generated based on the history, and this process is repeated. So this W layer and this W layer are basically the same. They are exactly the same, only the inputs are changing. So the layers are fixed, layer weights, but your inputs will change. Okay, so in this particular neural network, these YTs are the true labels. OTs are the ones which we want to match these YTs. In case of classifications, these are, you can think of these as the probabilities, and YTs are the true class probabilities, and you want these two to agree. Y should agree with O. So these are L's are the loss functions, and we have, for example, for classification, we are using the conventional cross entropy loss. Okay, so there are two things. One is training and one is testing. During training, we want to train the network for W's, V's, U's. These are all the parameters of the network that we want to train. We are given the labels Y's and the features XT's. So we train the network using gradient descent for these W's and V's. Once these are trained, in the testing step, there is no, I hope there is a figure on testing somewhere. So in the testing step, there will be no top two nodes. It's only going to be inputs and the outputs, right? These top two tiers, Y's and L's, they are only for training, because during training we are evaluating loss and trying to minimize it. Okay, once we have trained the network, then we'll just give it input sequence, and we will hope that it's going to return us the correct output sequence, which could be the labels of the classes, or in regression it could be some real numbers. Okay, so that's the setup of a recurrent neural network. So what we were doing last time, we were trying to compute the gradients. I just wanted to show you how this this recurrent neural network works. So I will show you what we did last time. I have it. So we drew this variable dependence graph. If at any time you don't hear, okay, so here is a variable dependence graph that we drew last time. All this is doing is we had this, let's see, we had this equation, set of equations that were relating hidden states and inputs to the new hidden states and the outputs. And these are the set of equations that we wrote last time. History and input goes through a layer W and U to generate an intermediate value AT, which passes through a nonlinearity, which is hyperbolic tangent, to generate the new state or the history of the network. Then we take this history, pass it through another linear layer. That gives us the outputs, OT, and the outputs are passed through a softmax function to generate the probabilities of the classes. Right? This is what we did last time. Now I wanted to set up a loss function which tries to make these predicted probabilities of the labels close to the true probabilities, which are one-hot vectors. So YTs will be containing the true probabilities. Y-hat-Ts are the ones that are containing the labels that are predicted by the network. So we had this loss function. You must be able to see it. We'll minimize this loss function. The LT over here is the loss function. The total loss function is the sum of all of these loss functions. So let's see. So here is, so you have L, which is sum of these LTs, and then let me fix my pen. This is the loss Next time I'm going to record it to avoid these glitches. So let's bear with me for today. So we have some of these loss functions LTs, and we sum it over T. LT was just this classical cross entropy loss function. And we wanted to minimize it over the parameters theta. Theta over here are W, V, U, and L. And we were trying to compute the gradients with these parameters. Okay. So in this process, we started off by drawing this variable dependence graph, which was relating the variable dependencies that you can easily see from these equations. So AT is dependent on BWH, U, and XT, and so on. AT is directly linked with HT, as you can see from equation 10.9. Then OT is related to HT, V, and C. And then you apply a softmax on OT to give you Y hat T. You compare Y hat T with YT to give you LT, which is the loss function at time step T. And then similarly, you compute the loss functions at every timestamp. So T plus 1 is a similar graph. So you can see there is one thing that goes from time T to T plus 1, that is the history. So that's one thing which links all these timestamps together. So that is visible in this variable dependence graph through this dotted line. HT goes into the T plus 1 layer, and you take this HT, you use it to compute AT plus 1, right? As HT minus 1 is used to compute AT, so HT will be used to compute AT plus 1. So you can see that in this particular equation that we wrote. HT xt plus 1 plus B will give you AT plus 1. So that's what is happening over here. This dotted line is giving you a link between HT and the variables at time T plus 1. So given this graph is basically going to guide us into writing the gradients correctly. So what I was doing was I was starting off by writing the gradients. So I wrote L is sum of LTs, as you can see. And then I started off by writing partial L over partial LT, which is trivially 1. Then I went ahead and started to compute the derivative of the loss function L with respect to OT. So I'm progressively moving behind this network, this variable dependence graph. First, I computed the derivative of L with LT. Then I will now compute the derivative of this L with respect to OT. So I'm moving backwards. That's what we did when we started writing chain rule. So now the derivative of L with OT, the ith component of OT, is by chain rule partial L over partial LT over partial OTI, which we wrote over here in red box. And as I mentioned last time, this is exactly the same calculation that we did in our previous handout when we were working with dense networks. So that comes out to be the true label, or the estimated label minus the true label. So that gives me if you stack this entire thing up, this gives you a formula for the gradient, which will be stacking up all of these components together. So the gradient of L with respect to the entire vector OT is going to be all of these components stacked together, which will just become vector Y hat minus vector Y. That's all it is. And then now I want to take it further back. I want to take the derivative of this L with respect to HT. Okay, since I have already taken the derivative of L with respect to OT, now let's go back one step further. Partial L by partial HT, that is exactly this gradient. And we had this formula last time that we derived, so when I go the convention. So the convention was this particular gradient of a scalar variable z with respect to a vector x is the derivative of the intermediate variable y with respect to x transpose the derivative of this z variable with respect to intermediate variable y. That's the formula that I'm going to use over here. So intermediate variable over here is, what is the intermediate variable between h and l? That's O. So I'll first compute the derivative of the intermediate variable with respect to ht, and then write the gradient of L with respect to the intermediate variable. So that's just an application of that particular formula that we had last time. So this thing, partial O tau or partial H tau, that was last time we saw it as just V. That's just matrix V. And if we put it together, V transpose gradient OTL. That's the derivative of H tau. So remember tau, what is tau? Tau was the last timestamp. So when I wrote, so here you can see what we were given was x1, x2 up to x tau, the values of the time series at different instances. And then we were given y1, y2, y tau. So the last time instance is tau. So at the last time instance, in this variable dependence graph, at last time instance, there is no path to the future because there is no future. There's no tau plus 1, right? So that's why the derivative of L with respect to tau is going to be different than the derivative of L with respect to tau minus 1 or tau minus 2. So tau, since it is the final timestamp and there is no future timestamp, so it has an easier derivative, which is just there is one path from HT to L. We don't have to consider the dotted path because that is the path to L into a future timestamp. Since for the final timestamp there is no future, so there is only one path that leads from H tau to L, and that is through O tau, right? So now for all other timestamps, delta in general, this gradient delta HTL, now T is not tau. In that case, you have two paths leading from HT to the loss function. One is through this dotted direction, and one is directly. So I'm going to take into account both of these directions. So I'm going to write it down. So the first direction is from HT to HT plus 1, from HT to HT plus 1. So this direction is, the derivative in this direction is partial HT plus 1 over partial T HT transpose, and then the gradient partial HT plus 1L. So that's one. What's the other direction? The other direction is directly from HT into L. And the intermediate node over there that I want to use is OT. So I'm going to just write partial OT over partial HT and gradient OTL. So that's the contribution from, this is the contribution. Number one is the contribution from this direct path. Number two is the contribution to due to the future timestamp in which the history vector is feeding. So this is the expression for gradient for a general time, for any general time index, which is not the final time index. So that's the expression of the loss function with respect to HT. Now you can tell me, try to figure out what is this value, partial HT over partial HT plus 1 or partial HT. So you can look at the equation. How is HT plus 1 related to HT? So it is related like this. Tangent hyperbolic AT, which is tangent hyperbolic B plus W HT minus 1 plus U of XT. Okay, that's how they are related. Sorry, not T minus 1, it should be HT, and this should be HT plus XT plus 1. That's how they are related. And now this derivative is simple. Uh, you can write partial ht plus 1 over partial ht as partial ht plus 1 over partial at into partial at over partial ht, just by chain rule. What is this? So the relationship between ht plus 1 and at is tangent hyperbolic. So the derivative of tangent hyperbolic is 1 minus tangent square hyperbolic. So this derivative is just, I'm not going to evaluate it. This is just this first. And the second one is, what is the derivative of at with respect to ht? That is just w, matrix w. So that is it. Now the transpose of this thing is, we want to plug it in over here. So we are going to get w transpose, and we have this 1 minus tangent square hyperbolic at. That's the first thing. And the second thing is OT over HD. What's the OT over HD? We have already done it. It is V. So the second thing is V transpose. And the gradient O tau L has already been computed. That is y hat minus y. So that's the overall gradient. Okay. And you can have it. This is 1 minus. So this thing is already, you know, this is just ht plus 1 itself. The square of it plus v transpose y hat minus y. That's the overall gradient with respect to h. Okay, so now we have all the intermediate gradients that I need to, for example, compute. Let's see, let's compute. We wanted to learn the parameters, so I'm basically interested in gradients like this. Gradient of the loss function with respect to a parameter v. So that gradient is just gonna make use of all these gradients that we have computed. So this is going to be gradient v sum over t lt, which is sum over t gradient v lt, which is simply sum over t. This we had done last time. There was one of the formulas that how does v depend on lt? V depends on lt. If you look at equation 10.10 in front of you, it depends on it, or you can just look at the computational graph. V depends on lt. Where is v? Yes, here is v. It depends on lt through ot. Okay, so if I want to write the gradient of L with respect to v, I have to consider the intermediate variable ot. So using one of the general expressions for gradients that I derived last time, conventions जो मैंने आपको I had given you, using that, this is equal to gradient of v oit, the ith component of oi, into partial L over oit. And if you, now mainly the thing that I want to evaluate over here is what is partial L over partial oit. That is unknown. So any guesses? Let me just to keep it different from, I will call it, let me index it by k. I want to use I for a different index. So that's what I want to find out. So what is this gradient? So that is simple. It's just going to be a scalar because L is a scalar, OKT is a scalar. So it's just bunch of simple. It's just simple derivative calculation. The other thing that we need to compute is, so I want to compute this. So this is a scalar variable, the kth value of kth component of output, and its derivative with respect to matrix V. So this is going to be a matrix, which is whose entries are partial V. So whose ith jth entry is this. So that's the matrix, the ijth entry of this matrix. Let me just write it like this to be more precise. So the ith entry of this matrix, ith entry of this matrix is just this. The derivative of the kth output with respect to ith entry of the matrix. That's the value of the gradient at ith. So that is, what is this? So to answer this, you have to just look at equation 10.10 and you will see that OKT is going to contain the elements of Vij only if k is equal to I. OKT is the kth component of vector O. So it's only going to contain Vij if k is equal to I, right? Otherwise, it's not containing that particular component. So this derivative is only non-zero when k is equal to I. Only non-zero. Otherwise, it is 0. So when k is equal to I, what is the value of this particular derivative? Anyone? When k is equal to I, what is the value of this particular derivative? What do we mean by, let's see, sorry, there's one mistake that happened over here. What do we mean by, so it's Hj, and where does the k go? Any guesses? Where does the k go over here? Let me write it more precisely. So where does the k go? So it's going to be a matrix which has 0 everywhere. At the kth row, k is equal to I, it will have a non-zero at the entry Hj for this particular derivative. And when you do it for all j, because it's only going to be non-zero when k is equal to I. For all other rows, you are going to have an I which is not going to be equal to k. So you're going to have zeros, 0, 0, 0. Only at a row where I is equal to k, you will have non-zero entries. And those non-zero entries will be just components of H. Right? So basically, this is going to be a matrix which is 0 everywhere. And the kth row has the vector H in it. That's what this gradient is. You need to understand it. That's what this gradient is for So this is what this gradient is if you stack up all I and j together. So here we did it for a particular I and j, and that was hj. But if you, since this is going to be non-zero only when k is equal to I, when you stack all of these entries into a matrix, you will see that it forms a matrix which has only one row, which is non-zero, and that row is, if k is 2, you will have h in second row. If k is 3, you will have h in third row, and so on. That's what is happening. So that's the gradient. So you have to be careful about what is happening. I have a bigger picture. So basically, in this summation over here, you have a matrix depending upon k, whose rows are h, whose one of the rows is h. So if the summation is k is equal to 1, you have first row of this matrix being h, k is equal to 2, second row of this matrix being h, and so on. So this thing is just a scalar, right? So you have, when you have k is equal to 1, first row is h multiplied by a scalar. And k is equal to 2, second row, same h multiplied by a different scalar, because the derivative of L with respect to O2t will be different from the derivative of L with respect to O1t. Okay, so if you stack this particular expression up, the gradient with respect to V of L is just the gradient vector OT of L. Sorry, this is not a vector. I have, yes. I'm not doing it. I'm summing it over k. This is what you are going to have. The outer summation with respect to t will remain there. The inside thing you will have OTL, that's this, and multiplied by HT transpose. That's if I stack it all up. The HT transpose, because this is the vector which is coming from here, this is HT transpose, this thing, and this thing stacked together for all k, it's going to be the gradient of OT over L. So that's the gradient of the loss function with respect to V. So we use the derivative with respect to O and others. Similarly, when you compute delta WL, you will use the derivatives that we have computed earlier, delta HTL or gradient HTL, and all these derivatives. So I've shown you one. You can compute all the others in a similar manner. And then once you know how to compute these gradients, then I can just, in this training, I'm going to take an L plus 1 iterate based on the Lth iterate minus the step size and gradient evaluated at V is equal to V. That's how you learn the parameters, V's, W's, U's, and B's and C's, all the parameters. So that's how you train. So this is called back propagation through time. The main gradient that shows you back propagation through time is this particular gradient. The history, the derivative of L with respect to HT is what was this? We have written it over here, W transpose. And then, sorry, we have missed over here one term. We had to write over here delta HTL. You can see this term, sorry, delta HT plus 1L. delta ht plus 1 L. Okay, so we had this term, gradient of ht with respect to L, of L with respect to ht is this matrix multiplied by the gradient of ht plus 1 with respect to L. Okay, so that's what we call, so the gradient of the history vector is back propagated. So once you have the gradient of L with respect to h tau, you will use it to compute the gradient of L with respect to h tau minus 1. Right, this is what this equation is telling you. That the gradient at next timestamp is used to compute the gradient at previous timestamp. This is exactly what this is telling you. So if I want to compute the gradient of this loss function with respect to h0, I have to back propagate this last timestamp gradient through all these stages to compute the gradient of the first history vector. All right, so that's back propagation through time, and it has some important consequences, positive and negatives, that we will see shortly. What are the advantages or disadvantages? But you need to keep this equation in mind, this top equation. I want to write it over here so that we can use it. So this is the equation, the key insight that we have. Anyways. So you have this equation in front of you. So that's the key equation, which links gradients at the last timestamp with the gradients with the first timestamp. Okay, so any questions at this time about this problems or some variations of this recurrent neural network? There is one variation of this recurrent neural network. Since you have seen from this expression that to compute the gradients, I need to basically, if I have to train this layer, for example, t minus 1th layer, I have to, what do I need to know? I need to know the gradients. What do we see from this diagram, this particular equation? We see that the gradient at the second layer depends on the gradient at third layer, and the gradient of third layers depends on gradient of the fourth layer. So if you want to train any layer, you cannot do it independently of the other layers, right? You have to train them together. So this is computationally sometimes extensive to back propagate this gradient all the way back to these previous stages to train them, right? So I don't want to, if you don't want to train them together, one of the way is that you make these hidden to hidden connections, as over here. You have to break them so that these variables don't depend upon each other. One way to do that is you can, instead of propagating these states forward, you can propagate these labels forward. What I'm saying over here is, instead of propagating ht minus 1 into ht, I don't want to use this information of the hidden state. I just want to use the previous label into the next hidden state. So what I'm saying over here is, if you want to predict uh, if you want to predict whether a sentiment of a sentence is good or bad, what I want to do is I don't want to look at the history vector of the sentence. I just want to look at the label of the just before this current word. So what did I think about this sentence just before the current word was written down, right? So this label is telling you about the sentence just before the current word. So before speaking the current word or writing the current word, probably you thought that this sentence is rude. So you had this label that this is a rude sentence, and you feed it to the next stage, and you will take into account the previous label and the current new word to again decide whether this sentence is rude or not, right? So maybe you don't need this history vector in some cases. You just need the true label and feed that in and use it with the current new word to judge whether a particular sequence belongs to a certain category or not. So that's, if you do this, then all these stages become independent, because y is basically given to you. It's a fixed thing. It's not a variable that you are, like h was a variable. Like y is just given to you. So once you feed y into ht, you don't need to train all these stages in sequence. You can train them in parallel, because all you need is the previous label, the current label, and the current xt to train this stage, right? So you can do it completely independently of the previous stage. But when these hidden states are connected together, to train this particular stage, you need to know the gradients backpropagated, because they are connected together. So variables are linked together. So if you break this link and make it dependent on the output label of the previous stage, that's one way to break this link and train these stages independently. I just wanted you to know this particular scheme of recurrent neural network is probably drawn somewhere. Let me see, where is it? So here it is. So you're just feeding directly the label into the next state. There is no connection from state to state. Right. So this is particularly called, is a special name for this. We call it teacher forcing. So you're forcing your next state, and you're telling it that this is the correct label. So this has its shortcomings. The output y, number one shortcoming is that during training, you can feed the true labels to the hidden states, right? Because you are given the true labels during training. But when you do testing, you are not given the true labels. So in that case, you can only just feed back your outputs to the next state. And you just hope that these outputs are close to the true labels. So it's not always the case that the outputs that the network predicts are close to the true labels. So in that case, the network during test time is kind of operating under different circumstances compared to the ones under which it was trained. During training, you were given the true labels, but during testing, you are not. So that's one problem which can make the network spit out wrong results. The another problem with this particular approach was, so let's see. One of the advantages is that you can now train in parallel. So that's one of the advantages. And there are then other variants of this where you can kind of mix and match. You can use mix of two strategies. In some stages, you can feed this output into this hidden state. In some other stages, you can use hidden to hidden states. Yes, so one of the other disadvantage of this was that history vector was somehow maintaining, it was capable of giving you diverse information about the history of the sequences. On the other hand, this label is giving you a very specific information about the previous timestamp. So obviously, there are differences between the two approaches. HT-1 over here could, in the best case, could be carrying a lot of information about very, very far off history, which you cannot expect from this particular configuration. So really using any of these configurations, whether using teacher forcing or history to history, it really depends on your particular application that you're working in. So from all these different connections, you need to know that recurrent neural network it's not a fixed thing. You can design your own architecture. That was one part of the reason that I went into some detail, so that you know that you can, according to your own application, you can build a recurrent neural network. You might choose to build a connection between outputs into the next histories or next states, or from previous state into next states. It just depends on your application. Okay, so that's all about. There are a lot of details of different architectures in this particular chapter. I won't go further into these details. Whatever I have given you already, it should be enough for you now to go ahead and read the contents of this chapter.